Okay, so can I start now? Good afternoon, everybody. Okay, look here, guys. Okay. So what I have done so far, number one, I explained data representation. I'm expecting that after this part, you understand, or we have different system for numbers. Also, you should know how can you convert between them, signed and unsigned, and so on. Is that okay? So on Thursday, there will be a quiz. This quiz is going to cover chapter 1. So maybe some of the question here in this quiz is how can you do this kind of convergence? Okay, just I want to make sure you understand it well. And also I explain for negative numbers, we use the 2's complement. Okay, that means if I ask you, give me, for example, -5. Okay, so all what you have to do, you can make binary for 5, which is 1 0 1 0 0 0 0 0. So someone can ask me why you put zeros there, because I'm assuming I'm storing it in a byte. So if I store it in a byte, it has to be this way. Okay, so this one is actually +5. So if it's easy to make it, right? Because the weight of this one is 1, the weight of this one is 4, and then all what you have to do, you have to calculate the 2's complement of this one in order to get -5. Is that okay? So to get -5, that first you have to calculate the 1's complement, which is 0 1 0 1, and then 1 1 1. Okay, and then you have to add 1. So it should be 1 1 0 1 1 1 1. Okay, so first you have to calculate the 1's complement, and then you have to add 1. Also, I explain if your number is unsigned, how can you convert the binary to decimal? If your number is signed, how can you convert it to decimal? In 2 cases, if it is positive or negative. Okay. For example, here, if this one is a positive, how can you know the number is positive? If it is unsigned, you can know from the most significant bit here. If the most significant bit is 0, that means it's positive. If the most significant bit, so this is -5, so it's 1, that means it is negative. And if the number is positive, the way you convert it very easy, 2 to the power 1, 2 to the power 2, 3, and so on. But if your number, for example, -5, and you want to convert this one to decimal, there are different ways, but what I prefer is you can calculate the 2's complement of this one. When you calculate the 2's complement of this one, you are going to get the positive version of this number, and then it's easy to convert to positive numbers. Okay, anyway, also I explained in this next section, I explained also you should understand if you have n-bit number, so if your number is n bits, should understand what is the range. What is the range of numbers you can represent in n bits if this number is signed or unsigned. And 2 to the power n is that how many numbers you can have in total. Okay. Also, I explained here if you have some characters, how are going to store these characters in memory, right? So actually, the way we store it, we store them in ASCII codes. Okay. Then I explained that we have a processor. This is a computer system. Any computer system should have this architecture, as I explained. Also, I explained we have input devices, we have output devices, we have memory. You should understand why we need memory, right? And that's also what we are going to see in the coming lab. We need memory simply because your program is going to be stored here. Also, your data. For any program, you have the machine code for your program. It is stored in memory, and also your arrays variables are also stored in memory. That's why you need memory. Okay. And also we have buses, common buses, as I told you before last time. For processor, I told you we have registers, and we have control unit and arithmetic logic units. For registers, as I told you last time, they are storage units. Okay, but there is big difference between register and memory. the similarity is both of them store data. That's okay, but big difference. Okay, so here memory is going to store your machine code and it's going to store variables, but registers they should help the processor to execute programs. Registers are inside the microprocessor. Memory is outside the microprocessor. Registers, we don't have many registers, maybe 5, 10, 12, 11, something like that. Very, very few registers. Also, registers are very fast, much faster than memory. If you remember in C language, we used to define variables, like for example, integer I, integer X, okay? That's we define variable. As you will see in this course, you have the choice. Sometimes you have the choice for sure. This variable, it can be a register. So I can use one of the register. I'm gonna consider this is X. Is that okay? Or it's gonna be a memory location. So I can take a memory location. I'm gonna consider this is X. Okay. That means every time you wanna write to X, you have to write to this register. If you wanna read X, you have to read this register, or you have to read memory location. One more thing you will understand better. Also, you understand it very well. Memory, in memory, we have too many locations, as you know, in memory. And in memory, every location is going to be addressed. It has address. It has a number. You got something what we call address. So if you want to read any location, you have to read it using the address. Okay? Address means like location number. But for registers, they don't have addresses. As you will see, okay, when I teach assembly, we're going to use their names, R0, R1, R2, and so on. So we're going to use names. It's their names, not numbers, not addresses, okay, as you will see. Yeah, so this is just a representation for memory. As you see here, we have address and we have data. Every location is storing a byte. So in every location, we store 1 byte. Is that okay? Every location has address, as you see here. So in address number 0, in location 0, in location number 0 or address number 0, we are storing this value, AF. In location 1, we are storing this byte, and so on. Is that okay? So one of the questions you need to ask, how big is the address? You are writing too many things here, yeah, because I'm assuming this one is a 32 bits. I'm assuming the addresses are, my address is 32 bits, but this actually can be different from processor to another. You got what I'm saying? So in some processors, this one is only 16 bits. Okay. In our processor, this one, the addresses are 32 bits. Is that okay? However, always, regardless of what processor you are going to use, in every location we store a byte. So this is something standard. Okay. So always in every location we store only 1 byte. But how big is your address? This can be different from processor to another. Okay. Also, you should understand the bigger the number, because I told you if you have n bits, how many numbers can you represent in n bits? 2 to the power n. 2 to the power n. Is that okay? So the bigger this number, the bigger is the memory. You got it. So I can address bigger memory. That's true, right? So if your addresses are 16 bits, that means we can address we can have up to 2 to the power 16 addresses, right? Or locations. But in case of 32 bits, it's going to be 2 to the power of 32, bigger. Okay. Any question, guys? Okay. Also, I told you we are going to have different types of memory. That's what we are going to use. We are going to focus on 2 types of memory: RAM or static RAM and the flash memory. Okay. Usually, what we do, we use the RAM. Usually, we use the RAM for variable, for your variable, for arrays. We use the RAM, but we use the flash memory for your program. Okay, so usually your program is going to be stored in flash memory, but all your variables are going to be in the RAM. So why we do that? Because the flash memory is non-volatile. Okay, that means if the power is off, still your machine can work. You understand what I'm saying? That is why I think one of the questions in the assignment I'm asking you, why any embedded system? So I'm going to explain later what I mean by embedded system, but for now, I'm asking a question, why any embedded system should have non-volatile memory? Okay, simply this is because you are going to store your programs there, right? So that if you disconnect, if you turn it off, if you turn your phone off and you turn it on again, it still is going to work, right? If you turn your GPS or any other small device, okay, your printer or any, if you turn it on, off and turn it on again, still it can work because your program is stored in a flash memory. Okay. One of the very important things, guys, and I'm gonna, okay, it's gonna be clear also in the future. I think I already, yeah. So here we have different types of data. So as I said, we have a byte, we have half word, which is 16 bits. We have one word, we have double word. Okay. So this is like containers. As you go here, we have bigger containers, so you can store bigger data. Okay, so your number can be bigger. Okay, you can store bigger numbers. But, and that's what a little bit confusing, but I'm gonna clarify it is, okay, so wait a second. Okay, I'm gonna wait. Look here. You told us memory is locations. Yes. Every location will store 1 byte. That's true. Okay. So if my data is a byte, that's very easy case. So I'm gonna store it in 1 location. That's very easy case. Is that okay? However, if your data is half word, how this one is going to be stored in data in the memory? You told us every location can store only 1 byte, but this one is 2 bytes. 2 bytes. So how I can store it? Okay, very simple. So what we are going to do, guys, we are going to take 2 locations from memory. So this one is going to be stored in 2 locations. Make sense? 2 locations. Okay. For example, this location number 0 and this location number 1. So this one is going to be stored at 0 and 1. Is that okay? However, we are going to use this address. We call this address, this is the base address. We are going to use this address to refer to this one. So what I want to say, although this one has 2 addresses, but we're going to use only the beginning address. You got what I'm saying? So we're going to use, so that means if I want to read a byte from location 0, so I'm going to read only this one. Or if I want to read the word, a half word, 16 bits from location 0, so I'm going to be 0 and 1. So always, you got what I'm saying? So always we use the base address. Same thing here, same thing. This one is 32. So this one is going to take 4 locations. 4 locations are going to come here. So sorry, it's the opposite. So here, this one is going to be stored in 4 locations. Is that okay? So in this case, we have address 0, 1, 2, and 3. Is that okay? Again, I'm going to use in programming, we're going to refer to this one to, when I say I want to read the word at location 0, it means 0 and 1, 2, 3. You got what I'm saying? So always we use the base address. Anyway, it's going to be clear later, but this is how it is. You understand? Any questions? And that's what we are going to see in the coming lab. So in the coming lab, you will see the memory, you will see the location, you will see how, you will see the addresses, you will see how in every location we store 1 byte. Okay. Also, I explained arithmetic logic unit. Yeah, and I just tried to give you some idea about a machine code, what machine code is. Okay, so you can think about this one is like a machine code. So machine code, for every instruction I'm going to teach in assembly, it should have a machine code. And that's also what you are going to see in the coming lab. Okay, so coming lab, you'll see the assembly instruction and the corresponding machine code. Okay, so the machine code is just a number. For sure, we're going to write this number in hexadecimal, but as I told you before, hexadecimal is just for us, just convenient for us. In reality, it's just 1s and 0s, a bunch of 1s and 0s. Okay, so what happens is that once you have these 1s and 0s, you put it on the hardware is going to do this operation. I just give you some idea here. And also, that's what we call instruction set. Instruction set. So every processor has an instruction set. An instruction set means This is all the instructions that the processor can execute. All the instructions, okay? Every instruction should have English word, okay? And this is what we're gonna use. And everyone, and that's what you are gonna see in the coming lab. So in the coming lab, you will see English instruction, and you will see the corresponding machine code, okay? This is in assembly, okay? And I think I made it very clear. Every instruction in assembly is executed by the hardware. Is that okay? Yeah. Also, I think you should understand what is the difference between high-level and low-level programming language. That's what we're going to do in the coming lab. You will see something like that, and you will see the corresponding machine code. You will see how they are stored in memory this way. Okay. Anyway, and also, as I said, the compiler is a very simple program, but the compiler is very complicated program because it's very far from the hardware. Okay? I think the best way to explain it is one instruction here. In order to do it, you may need 7, 10 instructions in assembly. Assembly is very detailed because you are programming machine by the hardware. What you are doing, the hardware will do it, right? But all this instruction cannot be done by the hardware, so they have to be converted to assembly, and that's what the compiler is doing. And usually compilers are not efficient, as I told you before. That's why if you want to do like very efficient program, very fast program, a program that doesn't take too much locations in memory, that's why we do it using assembly. Okay. Any questions? Anyway, so, and then here also I explain how programs are executed. So to execute programs, for every instruction, we have to do two things, fetch and execute, right? Fetch means I have to read the machine code from memory, right? I then execute it. Once I'm done, so I have to read the next one from memory, execute it. And also I told you there is a register. This register is called PC or program counter. This register should keep track. It should tell me it's like a pointer. You should understand it very well because, as I told you here in assembly, you are going to use a lot of pointers. Okay, so this is like one of the pointers. So PC, and that's what you should see in the coming lab. So what you should see in the coming lab, you will see PC is here. Okay, after you execute the instruction, you will see PC is updated to point at the next instruction. Okay? So I know. It's a little bit confusing, but hopefully you understand it well because we're going to use it all the time. You will understand, but let me clarify what I want to say. If you have a register, sometimes the value is set inside the register, the number, the data inside the register. Okay, that's okay. For example, you have X is equal to 2. So I'm going to use the register R0. I'm going to put here 2, for example. So this register is storing data or a value. Sometimes the value is stored in memory. For example, so this 2, so this is one case, okay? So this is not a pointer. This is not a pointer, okay? So you just have using a register as variable, okay? The other case, and that's what we are gonna see in this course. For example, R0 is gonna store like, for example, 0007. Look, so 007 is not the data. This is the address of the data. That's why you call it a pointer, because this one is pointing at the data. So this one is gonna point at location 0007, and then whatever is there, this is your data. Okay. So in this case, I call it a pointer. So if the register is storing okay, is storing address for the data, in this case we call it a pointer because it points. You understand what I'm saying? A very good example for now. But in chapter 2, we're going to have we're going to use it all the time because, as you will see in chapter 2, this is how we are going to read arrays. If you have an array, I'm going to use one register as a pointer to point at this location, right? So in this case, the register is going to store the address, right? Then after I read this location, if I want to read next element, so I'm going to increment the register to point at next one. You got what I'm saying? That's what we're going to do. So at least for now, don't worry about that. That's what we're going to do in chapter 2. But why I'm explaining it now? Because PC is doing the same thing. So PC here is a pointer, okay? And that's what you should see in the coming lab. So you see PC is not storing the machine code. PC is not storing the machine code. Instead, PC is storing the address of the instruction. And the coming lab, you should see how PC is updated. So I'm gonna give you a program. I'm gonna ask you to run it. For sure, I'm not expecting you understand the machine code yet, for sure. But I want you to apply everything I taught in this chapter in the lab and to see it. Okay, so you are gonna see. So I'm gonna ask you to execute one by one, instruction by instruction. Okay, so once you execute one instruction, you will see PC is updated to the next instruction. You will see the PC is updated. Okay. Anyway, so this is how it is. So all the time, any program is just a number of instructions. Instructions are stored in memory. For example, some instruction, it depends on the processor for sure. Some processor, for example, some instruction is going to take 2 locations, some instruction can take 3, and so on. But for our processor, actually, the instruction either they take 4 locations or 2 locations. You got what I'm saying? So maybe this is one instruction, this 4, one instruction, then another 4, and then 2, and so on. So some instruction takes 2 bytes, some instruction takes 4 bytes. Okay. Anyway, it doesn't matter. So what happens is that after we read this machine code, so PC should come to here. PC is going to update on the next instruction. Is that okay? So that's what we do, fetch. Next time we are going to do fetch. I'm going to read this one, and PC is updated to here, and so on. You got what I'm saying? So that's what you should see in the coming lab. So all the time, PC should help you to keep track of which instruction I have to execute. After you fetch, you just execute the instruction. Also, I explained the idea of clock. Okay. Anyway, so today I'm gonna focus more on our ARM processor, the processor we are gonna use. First of all, here I just want to make definition. I want you to understand. The difference between microprocessor and microcontroller. Microprocessor and microcontroller. Okay, look here, guys. As I explained before, microprocessor. Let me come here. Microprocessor is just one part of the system. So, for example, if this is a system, computer system, so microprocessor alone cannot make a computer system, right? Alone. So that's why we need buses, we need memory, we need input and output. So this is a computer system, okay? So processor alone is not enough, right? So you need other devices. This is microprocessor, right? What is microcontroller? Microcontroller actually is a system on a chip. So what happens is that we can have all these components in one chip. So it's a computer. Yes, it's a computer, just one chip. For example, this is chip here. Okay, so this chip is microcontroller. So inside this chip, it's a computer. So inside this chip, you can find inside the chip, you can find this system. Okay, and not only that, you can find other circuits. For example, you can have here timer system. You can have analog to digital converter and serial communication circuit. All of them just in one chip. You know what I'm saying? So, it's a computer system, and not only that. Inside this chip, there are RAM and also flash memory inside this chip. So it's a complete computer system in one chip. That's what we call a microcontroller. Okay, guys, any questions? Okay. So, okay, so now you understand microcontroller means you have a computer system, you have processor, flash memory, RAM, buses, and even other circuit, all of them in one chip. So how microcontroller are used? Actually, microcontroller are used everywhere in our life. Everywhere we use microcontroller. Okay. For example, microcontroller are using in all these devices. So everyone has a chip like this one. Okay, inside these devices. as in your car, there are many microcontroller inside your car. Okay, so the people are saying microcontroller, or and that's what actually. So we use microcontroller to create what we call embedded system. So we use microcontroller to create what we call embedded system. So what do you mean by embedded system? I'm going to tell you. So embedded system is a special purpose computer system, okay, designed to perform a dedicated function. Okay, so what is the difference between your PC and between embedded system? Okay, your PC is not embedded system because your PC is a general purpose. You can run any program, right? But here the microcontroller is an embedded it's used in embedded system means it's a computer, but this computer is going to do only one function. It's going to run only one program at all the time. Okay, for example, here in the GBS here we have a chip. This chip should run only one program all the time. You got what I'm saying? Same thing for printer. So it's a computer. It's a small little computer for sure. Why you call it little computer? Because you cannot compare it to your PC, right? Because you don't have the memory. The memory is small. The speed is small, and that's not a bad thing, by the way, because I'm not gonna run MATLAB or big programs on these chips. You got what I'm saying? So chips should do like a very simple functionality, very simple thing. So I don't need too much or very high competition, right? So it should be okay. Traffic light and so on. So the people are saying that using this microcontroller, we can make things smarter. The idea, the idea of smart things it became very attractive now. We talk about smart power grid, smart cars, smart. So how can we make things smart? Okay, actually, we can make anything in your life, like door, window, light, anything. You can make it smart if it has a microcontroller, and this microcontroller can run a program. That's it. So by running a program, actually, let me more accurate. So number one, if it has sensing, if you can sense something, if you can measure something, sense something, and then run a program and then take action. Okay, that's how things can be smart. So maybe I'm gonna show you only one example. Just I want you to understand. So this is the conclusion, guys. Based on what I taught right now, I want you to understand what I mean by microcontroller. Okay, microcontroller, as I told you, very simple definition. It's a complete computer system in one chip like this one, right? All what I have to do, just I have to connect input-output devices to this chip. That's it. Okay, so it's number one. Number two, and where it is used almost everywhere around us. Okay, because or anything you want to make it smart. Okay, so you can use this microcontroller because this microcontroller should have, or if you have a sensor, sense something, and then you have a program, computation is done by the microcontroller, and then you can take action. That's why I think it can be smarter. Okay. So you should understand what I mean by microcontroller. What should you understand by embedded system? Embedded system is a computer system, but it's not general purpose. It's just used for a certain function. Okay. So your microwave, it has a chip, right? So this chip is going to run only one program all the time. This program, we'll call it firmware. Okay. And that is why every embedded system should have non-volatile memory, so that if you turn off your GBS and you turn it on again, it still can work, right? Because your program is not in the RAM. Your program is in the flash memory, so it's non-volatile. Yes. Any questions? Yes.
I wanted to ask. So, you're saying microcontrollers, any systems? Or
no, I said this is a very good point. Okay, so microcontroller, it's a computer in a chip, right? So that means all the components of a computer in one chip, right? Why I'm saying that? Because your PC, if you open your PC, you can see the processor, you can see the RAM, and even you can take off the RAM, you can update the RAM, so you can see all the chips, okay? what we did, we put everything inside one chip. You got what I'm saying? Embedded system, it's a system, okay? It's a computer system that is used for a dedicated function. It's not for general purpose. So in these systems, we use microcontrollers. You know what I'm saying? So maybe I wanna, yeah, so I wanna just to give you some idea about it, how this microcontroller can make things smart, as we say, okay? I have a very good example here. We call it smart spoon, okay? So here you will see exactly what I have just said. If you have a sensor, if you can sense something, and you have a program, and you run the program, microcontroller, you run the program, then you can take smart actions, or you can take good actions. So I'm gonna run this video quickly, but there are, yeah. So I just want to tell you this embedded system are almost used everywhere around us. Okay.
For people suffering from Parkinson's disease, a disorder of the central nervous system, simply eating a meal can be an ordeal. The most common symptoms of the disease are related to movement. The basic act of getting food from plate to mouth can be difficult and frustrating. But now there might be a solution. Lift Labs, based in San Francisco, California, has developed a small device that tracks and compensates for small vibrations and tremors. Anupam Pathak, the founder and CEO, explains that the technology behind Liftware is similar to the image stabilization feature in high-end cameras. He spoke to VOA via Skype.
So what we've done is taken that same concept and applied it to a handheld device that would help people with a lot larger jitters. So somebody with a neurological disorder might be moving, up to an inch in magnitude. There's a little computer inside that's running an algorithm that would.
Little computer inside that's running algorithm, right? That's exactly what it is. So what happens here? You have a sensor. This sensor can sense the position of the spoon, okay, and then you can run a program, and then you can take a counter action. So if you make the spoon this way, okay, so I'm going to sense this action, and then I'm going to return it back. You got what I'm saying? So just an example so they put here like a small microcontroller. So it's just an example to understand how this microcontroller can make things smarter. Okay?
Would basically sense the person's motion, determine whether that was intentional or unintended, and if it's unintended, move opposite to what that motion does.
The result is that the device remains smooth and level despite the movement of the user's arm or hand. Food that would normally fly off remains on the spoon.
That just makes all the difference. I'm telling you.
Being able to see somebody eat, on their own for the first time, or even just eat better, has made it's a hugely impactful thing.
The device costs $295, but Lift Labs also accepts donations.
Okay. Okay, guys, any questions? Okay. Now, then we're gonna move to. Okay, so there are different types. There are different types of processors. Okay, so in this course we're gonna use ARM processor, and the reason for that is it's just widely used. Okay, for here I give you some numbers here. I used to teach a different processor, but this semester I changed it to ARM processor. Okay, the reason based on this number you can see there are a lot of it's widely used. Also, I give you some of the application or the devices we are using in our life, and they use ARM processors as well. Okay, so all of these devices are using ARM. That's why we have ARM processor. We're going to use ARM processor in this one. Okay, guys. So one of the things you should understand, computers or microprocessor, I can divide them into Van Neumann, and also so the architecture of computers, I can divide it into Van Neumann or Harvard architecture. The difference between them, as you see here, in case of Van Neumann, it's just a very simple processor. Okay, you can see here we put the instruction and data in memory, and we have only one pass. That means at any time you can read either instruction or data. You cannot read both of them at the same time because we have only one pass. However, Harvard is more complicated processor. As you see here, it has two passes here. That means at the same time you can read instruction, also you can read data. Is that okay? So the difference between them, this one is inexpensive. This one for sure it is fast because you can read data and instruction at the same time. Okay. So again, it depends on what do you want to do. Okay. So if the processor is slow, that doesn't mean it's bad, right? Right. It depends on how you are going to use it. Okay. So anyway, so here in ARM processor comes with different families. So we have different families. In this course, we are going to focus on family M. We have family A and other families. Okay. So this family, every family, it has different capability, different features. It can be used for different application. So here we are going to focus on family M, right? Inside family M, there are different numbers as you see here. So we have M0, we have M0 plus, and all M1. So these processors are using Von Neumann architecture. Also, we have M3, M4, M7, and so on. So we have different numbers. Okay. So again, everyone, the higher. So for example, M4 is more. It has more features than this one. Okay, and so on. So everyone has more feature, faster than the other one, and so on. Okay. Any questions? Okay. So as I told you guys, you have in the system you are going to use RAM. Also, we are going to use flash memory, RAM and flash memory. Is that okay? I told you what we are going to do. Your code is going to be written in the flash memory, but your data is going to be written in the RAM, and that's what you are going to see also in the coming lab. In the coming lab, when you write the assembly program, you make two areas: one area for the RAM, one area for the flash memory. Here in the RAM, you define all arrays or variables. Here in the area of the flash memory, you write your code here. So that's what you are going to see in the coming lab. So that's how we structure the assembly program. You are going to make two areas: one area for data, one area for RAM. So whatever you write here in the data, this one is going to be written in the RAM. But whatever you write here, this one is going to be written in the flash memory. Is that okay? For example, if you have something like that, all these definitions, all these variables can be in the RAM, or sometime, for example, this can be a RAM, or it can be a register. Sometimes this variable can be a register or RAM. However, the instructions themselves we are going to write in the flash memory. Okay. For sure, if you have the choice, okay. If you have the choice, so if your variable is stored in register, it's going to be much faster because the register are much faster than RAM. You know what I'm saying? So your program is going to be much faster if you have the choice. Any question, guys? Anyway, that's what you are going to see in the coming lab and in the coming lectures. In your program, I'm going to divide it into two parts: one part for data and one part for the code or instructions. Is that okay? Why you are making this way? Because this data is going to be stored in the RAM and the instruction is going to be stored in the flash memory. And I'm going to tell you the starting address. So we start from here. We start from a certain address, and every time you define arrays or variable, so it's going to go this way. And as you will see in the coming lab, the starting address is actually 2000000. Okay, so this is the starting address. For the flash memory, we have a starting address here for flash memory. Flash memory, it's the same idea. We start from a certain address, and every time you write instruction, it's going to go this way. Is that okay? In the coming lab, it's going to be 8000000. You will see that. So you will see that by yourself. So what's going to happen in the coming lab? You are going to go to this memory location. You are going to see how the machine code is stored from this location, and how your data is stored in this location. Okay, guys, any questions? Okay. So every processor should have a picture like this one. We call it a memory map. So what do you mean by memory map? So every processor should have a picture like this one. We call it a memory map. As I told you guys, we have here our addresses here, the addresses we're going to use in this course. And again, that's what you are going to see in the coming lab. Again, this may be different from one processor to another. So some processor, the address size is only 16 bits, right? Here, the address size is 32 bits, okay? 32 bits means if, I think I made a mistake here. Okay. I think I made a mistake, yeah. So 32 bits means starting, that means you can start from 8 zeros until 8F, right? Why 8? Because remember, if in hexadecimal, every digit is corresponding to 4 bits. So if you multiply 8 times 4, you are going to get the 32. You got what I'm saying? So if you have 32-bit addresses, so that means your memory, you should start from 8 zeros until 8F. This way. This is the whole range for the memory. Is that okay, guys? However, I'm not going to use all this range for memory. What do you mean? I'm going to tell you what I mean. Okay, guys. Usually what happens is that when you bring a chip, that's too much. So this is 4 giga. That's too much. You get what I'm saying? So actually what happens is that when you buy a chip, when you have a microcontroller, it's gonna tell you you should should know that inside the microcontroller, for example, it's gonna give you a certain amount for RAM, for example, 32K, for example, and 65K or 64K, for example, for flash, for example. You got what I'm saying? So for sure, this number is different from processor to microcontroller to another. Okay, so this is a RAM inside. So again, okay, let me make it clear. What I said is the whole range from here to here, from 000 until FF, 4 giga. However, this 4 giga is going to be used by different ways. I'm going to tell you how. Look here, guys. As you see here, for example, some addresses here, this is a range of addresses are used for flash memory. So there are some addresses, this part of the addresses are very used for flash memory. This part for the RAM, the internal RAM, because the microcontroller itself internally it has a flash memory and it has a RAM, right? Also, you can if you want, you can add external device. So you can add external RAM or external RAM. So if you need, you can add external RAM, and if you want, you may not need it. You understand what I'm saying? So in this case, if you do that, this will be the range of addresses used for external RAM. Not only that, even input-output devices, as you see here, input-output devices, as you will see in this course, also they have addresses. You know what I'm saying? So if I go back here, yeah. So if I go back here, guys, we have addresses here. So if you want to read a certain input device, it has an address. Okay. If you want to read a memory location, so you have to tell me which address. So in this case, so input-output device also has addresses, right? So the conclusion, what I want to say here, guys, is the following. Number one, every processor should have a map like this one. Usually, this is not something you can program. This is something manufactured. Okay, so you can you need to just follow it, follow this one. So what happens inside the chip itself? It has a RAM, okay, and this RAM should start from a certain location, and this is the whole addresses we have, and this addresses is going to be distributed this way. Some addresses are used for the internal RAM, some addresses are used for the flash memory. You can add some external RAM, and it's going to take these addresses. Also, input-output device is going to take also some other addresses. Any questions? For example, yeah, for example, if you have 4K bytes for memory, for flash, and maybe you have 256K bytes for data. Any questions? Okay. Now I want to talk about register for our processor. Okay. So now these are the registers we have, and again that's what we're going to see in the coming lab. So again, as I said before, registers are hardware inside the processor. You can see the registers. Okay. You will see the value of these registers. Okay. And as I said before, we're going to use this register either as a variable to store some data, or we're going to use them as pointers, right? And I'm going to clarify later, especially if you want to read arrays. In case of arrays, we're going to use them like pointers. Anyway, so as you see here, guys, all the registers we have are 32 bits. This number one. So they can store up to our 32 bits data. Okay, so all the registers we have can store 32 bits data. Okay, so as you see here, guys, we have from R0, R1, R2, R3. This is the name, and in coding and programming, we are going to use this name. We're going to use these names. So on Thursday, you will see these names in the program. Okay, so R0, R1 until R12. Okay. Is it from R0 until R12? This part we call it general purpose registers. You can tell from the English name, they are general purpose, so you can use them for whatever you want. They don't have a special functionality. They are general purpose. Is that okay? Every one of them can store 12 bits. Actually, from 0 until 7, this one we call it low registers. And from 8 to 12, we call it high register. But all of them are general purpose. Okay, general purpose again means you can use it, right? So it doesn't have a special functionality like PC. So PC has a special function. Okay, you cannot. It's not general purpose. Okay, so why you call this one low registers and why you call this one high registers? This is because some instruction can only work on this register. Some instruction can work on all of them. Okay, so some instruction can only use this registers. Some instruction can use everything. Okay, guys. Okay, so for the other register, we call them special purpose register. For the other. So as I told you before, we don't have many registers. That's always the case for any processor. We don't have too many registers. Okay. So here we have a special purpose registers. For example, for now, at least we know one of them. One of them R15. R15 is actually PC, program counter, and that's what you are going to see in the coming lab. You will see how every time you execute one instruction, you see how the PC is using as a pointer. So our PC is always storing the beginning address of the instruction that you are going to execute next. After I finish this instruction, I'm gonna bring it from here. Why you say the beginning address? Simply because, as I told you, because the instructions we have instructions stored in 4 locations. We have instructions that are stored in 2 locations. Okay, so PC always you will see it's gonna point at the beginning one. You know what I'm saying? You understand what I'm saying, guys? So what I want to say here, if PC is pointing here, and this is a byte, But if I want to read the 16-bit from here, have a word, so I'm going to take this one and next one. But I'm going to use only we call it the base address. Okay. Same thing if you want to read a word 4 bytes. Okay, so that's what you are going to see is going to be only point at this address. So at least we know one of them. Later, I'm going to teach you also stack pointer. Stack pointer is similar to PC, but this one is pointing at the top of the stack. So we have something we call it a stack. I'm going to teach you later in details. So PC is SP stack pointer is also storing an address. And this address is pointing at the top of the stack. So every time you write to stack, stack pointer is updated. Every time you read from the stack, stack pointer is updated. for sure, I'm gonna teach later why we need what is a stack and why we need it. Okay, so that's what I'm gonna teach later. So this is R13. So now quickly, I don't want to spend much time here because this one I'm gonna explain later in details. So here a stack is first in, first output data structure. Okay, we're gonna use it to store local variable and pass arguments to subroutines. So when the subroutine comes, I'm gonna tell you how can we use this one. In order to know what is the location of the top of the stack, we're gonna use, so this one is a special purpose. This one is storing address, right? So this is a pointer. Okay. We have other one here. We call it link register. So this one is storing the memory address of the instruction that needs to run immediately after a subroutine is completed. So you remember, for example, if you have here, if you call a function, if you go to a function, after you finish a function, you have to come to here, right? So you have to know, you have to store this address so that you can come to here. So as I'm going to explain later, this one should help should help to find the return address where you have to return after you execute the function. Is that okay, guys? As I told you here, guys, in our processor, we have each instruction, then and also that's what you are going to see in the coming lab. So in the coming lab, you will see some instructions are for 32 bits, some instructions are 16 bits. You will see, because you will see the machine code for every instruction. You will see some instruction 2 bytes, some other instruction are 4 bytes. Okay. Again, this is not something fixed, guys. If you change the processor, maybe they are using different. It's different. Sometimes instructions are 3 bytes, but it's still the same concept, the same idea. Yes.
Is there a reason why the naming is different from, I don't know, just from 1310 and C++? First in, first out was a queue, and the stack was first in, last out. So is there a reason why the naming is different?
No, the naming should not be different. Maybe there is a mistake here. I think.
Queue is first in, first out.
Yeah, I think that's a typo. I'm sorry. I'm gonna correct it. I'm sorry. Yeah. No, Q is first in, first out. It's like a line. This is a queue. Yeah. This one is last in, first out. Last in, first out. So I'm sorry. Thanks for letting me know. So I'm gonna correct this one. Okay. So stack is any stack. Okay. It shouldn't be different, right? So I'm sorry. Thanks. So I'm gonna correct this one. So stack is the data structure for last in, first out. Okay. We have other special purpose register that are using. We are going to use them later in something we call interrupts. So when we talk about interrupts, we are gonna explain these registers. Also, we have a very important register. I mean, maybe I'm gonna spend some time on this register, special purpose register. It's called this one. Okay, so this register, XPSR or program status register, Okay, guys, we have a status register. This register is storing what we call flag bits. Okay, I'm gonna spend some time on it here. Okay, guys. So we have this register. This register is storing the flags. So this one are storing flags. So please tell us. What do you mean by flags? Why they are important? You will see them in the coming lab as well. Okay, so every flag. So here again, guys. So we put all the flags in one register. This register is called XPSR. Okay, so every bit is a flag. Every bit is a flag. So what do you mean? So flag is a bit. That's true. Every bit is a flag. Okay. Okay, so that means every bit should be 0 or 1. If it is 0, it's telling you something. If it is 1, it's telling you something else. And every bit is independent. So here in this register, every bit is independent. Okay, so this is a flag for something. This is a flag for something else. This is a flag for something else. This is a flag for something else. For now, I'm going to focus on 4 flags. Okay, let me say it again. We have a register, a program status register. in this register, we store flags. Flags are very important. Flags are very important in order to make conditions. You remember in C language, you can make conditions something like that. If A is equal to B, okay? So how can the hardware can make something like that? Flags. So flags should help the processor to make comparison like this one. This number one. Also, flags are important to know if there is overflow or not. So for sure, I'm going to explain what to mean by overflow and how flags can help the hardware to do conditions, something like that. Okay, but for now, we should understand we have a register, we call it program status register. In this register, every bit is independent, it's different, right? So, and every bit is a flag. Every bit should be 0 or 1. If the flag is 0, it means something. If the flag is 1, it means something else. Is that okay? So I'm going to give you now, I'm going to give you some more information about these flags. I'm going to focus on 4 flags now, okay? So for now, I'm going to focus on 4 flags. The first flag is called 0 flag. Zero flag. Okay, so just 1 bit, we call it 0 flag. Okay, guys. Again, this bit can be 0 or 1. Okay, we should understand that these flags are updated automatically after executing every instruction. So after you execute the instruction, the flags are updated automatically to give you some information about the status or what happened in this instruction. Okay, let me, can you clarify? Okay, I'm gonna clarify. Okay. So for example, 0 flag, if you execute an instruction and then you find the 0 flag is 1, what it means? It means the result of this instruction was 0. You can tell from the English name. Okay, so for example, if you are doing subtraction or addition, whatever, and then you want to add or subtract 2 numbers, and then you are going to get the result here. If the 0 flag is 1, that means the result is 0. The result of the operation was 0. You did some operation and the result is 0. Automatically, it's going to be updated. It is 1. So if the result is not 0, it's going to be 0. The 0 flag is 0. So again, the 0 flag is just 1 bit. This bit is going to be updated automatically after you execute every instruction. And that's what you are going to see in the coming lab. What you're seeing in the coming lab, after executing instruction, flags are updated. Okay. So one of the flags is the 0 flag. 0 flag should tell me if the result is 0 or not. Okay, guys. And this can be used for comparison. This can help us for comparison. For example, if I want to do something like that, if A is equal to B. If I want to do something like that in assembly, and that's what we're going to do in this course. Okay? To do something like that, we're going to do it using 2 instructions, not 1 instruction, 2 instructions in assembly. Number 1, I'm going to do subtraction. Oh, I want to compare. You do subtraction? Yes. So number 1, I'm going to subtract. So I'm going to write an instruction to subtract. That's what we're going to see in this course. That's how can we make condition like this one in assembly. We do it using 2 instructions. Number 1, you subtract. And then after you subtract, this one is going to update the 0 flag. Automatically, it's going to update the 0 flag. After that, I'm going to use a branch instruction. This branch instruction is going to branch if the 0 flag is equal to 1. Otherwise, it's not going to branch when the 0 flag is equal to 0. Okay. So how can we make comparison? You got what I'm saying? So number 1, you do on the hardware, you are going to do subtraction. Once you do subtraction, the hardware is going to update the 0 flag automatically. It's number 1. Number 2, you are going to use a jump instruction. This jump instruction is going to make the decision to jump or not based on the value of the 0 flag. That's why you do subtraction here, because I want to update the zero flag. I want to update the zero flag so that this instruction is going to use the zero flag. So conclusion, make it easy. I'm going to make it looking good. We have a register. This register is called the program status register. Okay. This register has every bit, we call it a flag. Every bit is independent. Every bit should tell me. Also, these bits are updated automatically after every instruction. So after execute an instruction, they are going to be updated. Every flag should tell you something about what happened in this instruction. One flag I explained right now, we call it zero flag. So the zero flag, if for example, if I do subtraction, and then you found that zero flag is 1, what it means. So this flag is updated if the result of this instruction is 0. And this flag is 0, this flag is 1 if the result is 0. Otherwise, it is 0. Flag, right? So flag, when you raise a flag. Okay. So this flag should tell me if the result is 0 or not. And I give you one example here. How I can use this one? I can use it for something like comparison, as I did right now. Number one, you do subtraction. Okay. Once you do subtraction, now I'm going to look at hardware. Hardware is that's how the hardware can do jump, right? So the hardware circuit is gonna, after you do subtraction, the circuit is gonna take the zero flag. Okay, it's gonna connect zero flag. If the zero flag is 1, the jump will be taken. Otherwise, not. Yes. Okay, guys, let's move to the next flag. Okay. The second flag I want to talk about, we call it negative flag. N flag. Okay. So in case of the negative flag, this negative flag, if the result of the operation, again, these flags are updated automatically after the execution of every instruction. If the result of the operation or this instruction, if the result is negative, so the zero flag is going to be 1. So the zero flag is 1 when the result is negative. And the zero flag is 0 when it is not negative. Not negative. Not negative means 0 or positive, right? So this zero flag should tell you if the result is negative or not. If 1 means the result is negative, right? Remember, if you have a number, this bit, the most significant bit, can tell you if the number is positive or negative, right? So actually, if this is the result, if the result is stored here, so actually, if this one is 1, that means the number is negative and the n should be 1. And if this one is 0, that means the result is not negative and n should be 0. Okay, so they are aligned together. Yes. So this actually so easily you can just copy the most significant bit of the result, just to put it in n. You got what I'm saying? So again, the n flag, negative flag, should tell you if the result of the instruction you did, if the result is negative or not. If it is 1, means it's negative. If it is 0, so means the result is not negative. So, and this is exactly how if this is the result, how I can know for the most significant bit, right? If the number is negative or not. So actually, yeah. So actually, you can just copy the most significant bit, put it in n, and this is n. Okay, any questions? Okay, guys. Now, so again, I explained zero flag. If the result of the operation is 0, the zero flag should be 1 to tell you the result of this operation is 0. Negative flag, if the result of the operation is negative, okay. So negative flag can tell you it should be 1 to tell you. Is that okay? And flags again, hardware. They are hardware circuit. They are updated automatically, right? The hardware circuit will update them, and that's what I'm gonna ask you to observe in the coming lab. So in the coming lab, I will ask you, after execute every instruction, you will see the flags are updated based on the result of the instruction. Okay. Now we have 2 more flags. I'm gonna explain. We have C flag, which we call it the carry flag. And we have another one with V flag. So this is C flag, and we have V flag. This one we call it overflow flag. Okay, guys. Okay, what are these flags are used for? Okay, I'm gonna tell you. These two flags together should help you to know. These are flags to know if there is overflow or not. If there is overflow or not. So these two flags should help you to know if there is overflow or not. Okay. If your numbers unsigned, so the C flag is gonna tell you. So this one is used for unsigned overflow. And this one is used for signed overflow. Okay, wait a second. You are telling us there is something, it's called overflow. Still, I didn't explain what I mean. Yeah, that's okay. There is something called overflow. That's okay. And these two flags should help you to know if there is overflow or not. That's true. If your number's unsigned and you want to know if there is overflow or not, look at the carry flag. But if your numbers are signed and if you want to know if there is overflow or not, look at the V flag. Is that okay? But tell us, what do you mean by overflow? I'm going to tell you what you mean by overflow. Look here, guys. If this is a byte, if I add it to a byte, and I want to store the result in a byte. If I want to do something like that, I want to add 1 byte to 1 byte, I want to store the result in a byte. Is that okay, guys? First of all, before I continue, what is the meaning English word overflow? Too much, or I'm going to say it in a different way. You exceed the limit. There is some limit and you exceed the limit. This is the meaning of overflow. That's true. That's true. So that means we have a limit, and when you exceed the limit, overflow happens. That's true. So, okay, so what is the limit? I told you before, there is a limit. For byte, if your number is unsigned, your limit is you can store from 0 until 255. That's your limit. I cannot store more than 255. It's not enough. Too much. You got what I'm saying? This is the limit. If your number is unsigned, so my limit is -128 to +127. This is the limit, right? I cannot store more than 127. I cannot store less than -128. This is the limit. Okay, guys? Okay. So again, overflow means you exceeded the limit. And limit means if your number is a byte, there is a limit on how much data or how big the number you can store in a byte. It's a limit. Okay. So now, what do you mean by overflow? I mean, I want to add a byte to another byte, and I want to store the result in a byte. I want to add a byte to a byte. I want to store the result in a byte. It may happen that this result is going to be bigger than a byte. And at this time, overflow happens. For example, if I want to store 255, which is 1111111, 255, okay? If I want to add it to number 1. So here, I want to add, this byte is storing 255, this byte is storing a byte. I'm assuming this number are unsigned. Okay, I want to add them together. So the result should be 256. And 256 means 100000000. This is 256. So this one is overflow happens. You got what I'm saying? Because you need more than a byte. I cannot store the result in a byte. So what you are gonna get? So what you are gonna get, actually, you are gonna get 0000000, and for sure the one is not gonna be stored. So here, when I add 255 plus 1, I get 0. The result is 0. So always, when overflow happens, I'm gonna get wrong result. Always. You get what I'm saying? Simply because overflow means I don't have enough space. I don't have enough space. That's why you are going to get a wrong result. So when I add 255 plus 1, and someone may be confused because in digital system, when you add number to a number, this is the confusing part, or this is what you should understand. I'm not adding number to number. It's not numbers. I'm adding a hardware byte to hardware byte, and then I'm gonna store the result in a hardware byte. Okay, so in digital system, if I ask you to do this calculation, you are gonna say, yeah, okay, it's sorry, it is 0, 0, 0, 0, 0, 0, 0, add 1. Okay, that's okay. This is okay when you work on numbers, but now keep in mind you have containers. I have a container a byte, and then I am gonna store the result in a fixed size container, which is a byte. Okay, guys. So in this example, here, after you add this byte to this byte, you are gonna get 0. So always, if there is an overflow, always the result is wrong. Okay. So now the question, I'm gonna say it again. The question is that how if your numbers are unsigned numbers, if your numbers are unsigned numbers, if you want to know if there is overflow or not, carry flag. If the carry flag is 1, that means there is an overflow. Okay. However, if your numbers are signed, V flag should be 1 if there is overflow. It may happen that you have unsigned overflow, but you don't have signed overflow, or you have signed overflow, or you may not have unsigned overflow. It depends on the numbers. Okay, so someone can ask me, why you don't have only 1 flex? Why 2? Because these are 2 different cases. Because the limit in case of unsigned number is different from the limit in case of signed numbers. Limit is different. So these are 2 different cases. So maybe you have, if your numbers are unsigned, you may have overflow, but if they are signed, you don't have, or maybe you have for both of them. So these are 2 different cases. So again, so these 2 flags should tell you if there is overflow or not. One flag is used for unsigned overflow. The other one is used for signed overflow. The problem is, as I told you, when you add 1, 1, 1 plus 1, 0, 0, 0, you are not going to get error. So you are going to get some result here, but this result is not correct. So the operation will be calculated. You are going to get result, but this result is not correct because of the overflow. Okay, guys? Okay. Now, so if you are running your program, if you want to know if there is overflow or not, very simple. Just check these 2 flags. Is that okay? However, if you want to know, not program, you yourself, okay? If you have numbers and you want to know if there is overflow or not, how can you do that? Okay. So if I give you a question, and that's what I will do, and that's what is in the quiz. So in the quiz, I'm going to give you numbers. I'm going to tell you is there overflow or not. So how can you know if there is overflow or not? Okay. There are 2 ways: difficult way and easy way. Okay. The difficult way, and I don't recommend it for sure, but I'm totally fine if you want to use it. But I have easier way anyway. So the difficult way is do the calculation and see if the result is correct or not. If the result is correct, for sure there is no overflow. You understand what I'm saying? But it's not good way because you have to do a lot of conversions. So it's gonna take some time from you. But anyway, there's an easier way. Okay. The easier way is that if you add numbers, look here, guys. One plus 1 is 0, and we have 1 here, right? 1 plus 1 is 0, and we have 1. 1 plus 1 is 0, and we have 1. 1 plus 1 is 0, and have 1. 1 plus 0, 0, 0, and then there is a carry here. Whatever you get here, so if there is a carry resulted from the last bit here, so this one will store in the carry flag. So if your numbers are unsigned and there is a carry generated from the most significant bit here, so this one will be in the carry flag. You get what I'm saying? So again, if I give you a number and I'm asking you, if your numbers are unsigned, is there overflow or not? All what you have to do, just do addition, 1 plus 1 is 0, and then if there is whatever you are going to get at the end here, this will be the carry flag. Okay. So if I get 1 here, if there is 1 here, that means the carry flag should be 1. It means there is overflow. If nothing is here, so C is equal to, okay, C is equal to 0. Any questions? Yes.
So right here, you're adding 2 unsigned unsigned numbers.
Yes.
That's why it goes to C. So if either or both of them is signed, does that mean that it should always go to B? You know what I'm saying?
I got what I know this confusing, so listen to me. What we do is the two numbers are signed or unsigned, so it can be mixed, right? So regarding this point, listen to me. I know this is confusing, but that's why I want to clarify first. I'm gonna continue it next time, but I want to clarify for now. Listen to me. So someone, I told you, the hardware is gonna give you carry, it's gonna give you overflow, right? If your number unsigned, the carry is 1. If your number is signed, the overflow is 1. That's okay? And I told you before, the hardware doesn't know if your number is signed or unsigned. This is something that the programmer has to consider in your program. So please tell me, if the hardware does not know signed or unsigned, how the hardware is gonna do the overflow, signed overflow and unsigned overflow? You know what I'm saying? Very simple answer. What's going to happen? The hardware is going to give you the two options. The hardware is going to consider the number unsigned and then calculate the carry. The hardware is going to assume the number signed and give you V. And then you, as a programmer, in your code, if you consider your number unsigned, so you're going to check C, not V. And if you consider your number signed in your code, you have to look at V, not C. The hardware doesn't know. That's why the hardware is going to give you both V and C. Same thing for the negative flag. You remember for negative flag? Negative flag, what if my number is unsigned? You got what I'm saying? What if my number is unsigned? If your number, again, when you calculate the negative flag, so it's going to consider your number is signed and it's going to give you this one. You got what I'm saying? So again, I know that I'm gonna read next time in this part, but for now, you should understand. Number one, the hardware doesn't know the number signed or unsigned. The hardware is going to give you the two answers. If your number signed, it's going to update V. The hardware is going to consider number signed, update V. The hardware is going to consider the number unsigned, update C. And it's a two option. And then it's up to you in your program. Are you going to look at this one or that one? The hardware is going to give you both of them. Yes.
I have a question about the homework. How do you want to turn that in?
No, just no. Write in a piece of paper, okay, and turn it during the lab. We're gonna create it and return it to that. Okay, guys. See you next time.